Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
So, hi everybody. Thank you very much for joining us at almost the last session of CppCon 2021. We are going to talk about algorithmic complexity. We are part of the Back to Basics track. We would start with things that probably most of you know, but we will try to touch some nuances and important stuff that I think we should discuss. Why this talk? Well, it all starts with performance. Performance is the name of the game. We are in C++ because we want performance. And in a way, algorithmic complexity is about performance. You all hopefully know that linear complexity is better than quadratic. O of n is better than O of n square. But that's only the start, and even that is not necessarily true all the time, because it might be that we would prefer a certain algorithm which is worse on the worst case, but better on the average case. So we would discuss that. There are still important stuff that might be overlooked that we want to discuss, and as already mentioned when talked about O of n versus O of n square, the academic answer isn't always the practical answer. So in some cases, we may see some complexity which is better, and still we would prefer to do something a bit differently for other considerations. A few words about us. So, my name is Amir Kirsh. I teach at the Academic College of Tel Aviv-Yafo, and I'm also a developer advocate at Incredibuild. At Incredibuild, we do build acceleration. So if you have slow builds or big builds of C++ code, feel free to discuss with me later. And I have with me my co-speaker, Adam, who is also from Incredibuild. And I think that, Adam, you can join. We are going to talk about, let's start with performance, algorithmic complexity.
Well, performance, it's not just, you said that performance is the name of the game?
Yeah.
But it's not just performance. Okay, so it's not just the performance. There's actually something bigger than just performance.
What can be bigger?
Well, scalability. Scalability is bigger. If you think, say we have a good algorithm that, we have database and it works well, we're happy with the performance, we have gigs of data and it works well. But what happens next week if we have terabytes of data? And what happens a year from now if we have peta or zeta?
Okay, so scalability is important.
Yeah. Okay, so maybe before we speak about that, let's speak about computational complexity, or the complexity of algorithms. Basically, we're interested to know, giving an input of size n, what is the amount of resources that we would need to run the algorithm. It could be the amount of time, it could be storage, or it could be any kind of other resources. Okay, to make things a little bit more formal, say we have an input of size n, we would think about the function f of n as the amount of resources that are required to run our algorithm. We would denote t of n as the time or the number of elementary operations that are required to run the algorithm, and s of n to denote the amount of space that is required to run our algorithm. Well, it's easy to see that for most of the algorithms out there, giving an input of size n, it would need different amount of resources for different inputs. So we would have to be a little bit more precise and say, if we're discussing about the worst case complexity, the average case complexity, or the best case complexity, which would be obviously less important for us. Just to get a little bit more formal, but still not too much, we would say that f of n, the amount of resources that our algorithm requires to complete, is O of Gn, if there is some constant k such that for n that is large enough, f of n is bounded above by kgn. Okay, so it's an upper bound. And we're basically interested in the asymptotic analysis. So let's go to an example. Say we have this algorithm, and this is the amount of time or elementary operations that the algorithm requires. So here we have k n log n plus k n. It's clear to see, right, that when n tends towards infinity, n log n becomes the dominant factor, right? It dominates over both constants and even the linear component of this equation. So we would say that this is an n log n algorithm. Well, there's, the big O notation is a part of the Bachmann-Landau family of notations, of asymptotic notations. Here, maybe it's important to mention that big O is an upper bound. So being such, it doesn't necessarily have to be tight. So in many cases, if we can say theta of Gn, which means that Gn is both the lower bound and the upper bound of the amount of resources that our algorithm requires, then it would be more precise, but for the purpose of this talk, and as it is, we usually do in the industry, we would just mention O, big O notation, and we would try to give a tight bound.
So let's let the charts talk. Let's see some examples. Suppose we have an operation which is not related in its complexity to the actual size of the data. So we have constant complexity, and we call it O of 1, which is pretty good for scalability. It means that we do not need any additional resource, even if we have more data. Even if the complexity is logarithmic, which means it is O of log n, we are still in a good place because the amount of additional resources that are needed are less steep than the amount of data that is added. And you can see that on the graph. When we reach linear complexity, and it doesn't seem quite linear on the graph, can you see why it is linear even though it is not a straight line? Yes, that's correct. We have an answer there because the y-axis are logarithmic. So the linear complexity means that, well, you add data, you pay for the additional data in a linear trend. When we reach n log n, then again we are a bit above that, and there are algorithms that require n log n complexity. When we go for polynomial like n square or n to the power of 3 cubic, then again the chart goes up in a much more steep trend. But then when we go to exponential or factorial, then we are really in troubles because, well, it would not hold. You can see that even if we reach 20, 30, the data is too big to allow computation, either if it is in time or in space. Now, it might be that we got it. It might be that there is a need for something that would demonstrate it even better, which is the actual time estimate. So let's take the actual time estimate. Suppose that the initial step is a microsecond. And microsecond is quite a lot, but even if it is less, then you can divide the numbers here by 10, by 100, and still get the same order of numbers. So if we are with constant complexity, well, it is 1 microsecond for any amount of data. But when we go, for example, for polynomial, we can see that if we reach 1 million, we should wait 12 days. Well, 12 days might be fine. It depends on the actual operation that we want to do, but it might be too much. You know that in the academia, usually we talk about the family of polynomial complexity. And you can see that in actual practice, there is big difference between the n square and n to the power 3, between cubic and square. So, for example, if we have 1,000 cases, n square might be still possible in 1 second, whereas if we are with a complexity of, I would say, 3 nested loops, if we get it as n to the power of 3, we are on 16 minutes. So all the red part of this table, which goes to trillion centuries, by the way, if we are on exponential algorithms, are quite bad. We do not want to reach them usually. Let's see if we got it right. Are you ready for a short quiz? Yeah, let's do that. Okay, so what is the complexity of getting an element in a vector at index I? Yeah, here the answers are pointing to constant O1. Yeah, because vector is random access. Okay, what is the complexity of getting an element in a list at position I? Well, a list is not random access. You have to iterate in order to reach the ith element, and this means O of n, right? Linear. Now, in order to see that a bit better, let's do a simple benchmark. We actually do not need to do a benchmark in order to see that, but it's nice. So I prepared the benchmark, and it looks like that. I'm using here QuickBench, which is an online benchmarking tool for C++, and I have here for both a vector and a list the actual results, an actual run for which QuickBench allows you to see the results for a range of data sets, a range of data size. So the data points that I use here are 8, and then it should be, I think, 56? 64. 64, yeah, sounds reasonable. And at the end, 256. And you can see, well, it's linear. The list is linear. It's actual data. It's not a linear line that I drew by hand, and the other one is constant. So yeah, this is the benchmark, and we see that theory comes to actual numbers. This was I in a list. Okay, next one. Pushback to a vector. What is the complexity of pushback to a vector? Adam, what do you say?
Well, we might have capacity, right? The vector has capacity, and we just push it back. So it would be constant.
But maybe there isn't.
If there isn't capacity, then the vector needs to be resized. Then it would be linear, right? We need to allocate new memory. We need to copy or move the data, and then it's linear.
So is it linear?
I guess.
Linear if we do not have enough capacity, then we have to allocate. If we do not have enough capacity, we need to allocate. If we have capacity, well, just add it at the end. So is it O of 1 constant or linear O of n? Because you need to reallocate, copy, or move the entire thing, which means copy or move the previous n elements. Is it in the worst case? We're asking about the worst case, not the average case. Well, if you remember, pushback to a vector, is it worst case On or O1? Well, we have to speak about amortized complexity. Amortized complexity is a tool for discussing worst case scenario, but when looking at more than just one case, more than just one call. So we want to amortize more than one specific call to push back into a vector. Now, let's take a few examples. Suppose that the total n operations for a certain specific algorithm take, in the worst case, O of n. So it means that if for n operations, for the entire n operations, the total worst case for all n operations took or should take O of n, it means that the amortized complexity for a single operation would be O of 1, constant. And example 2, if the total worst case would be quadratic, then it means that for a single operation, it would be amortized O of n, which means linear. In our case, we have to analyze that. Can we say that pushback to a vector would be amortized O1? Well, I think we can. We will check that in a moment. Just to note, amortized complexity is not the average complexity. It is used mainly for worst case analysis. By the way, from a paper quite recently, not too ancient, from 1985. So, pushback to a vector is amortized O1. So if you try to understand how much it costs you, well, it is perceived as constant. How can we tell? Well, mainly because the specification says so. The specification requires vector to have amortized complexity, constant amortized complexity for pushback. And then the implementers have to oblige, have to implement accordingly. How can it be done? Well, we'll see in a moment, but it's not only for vector. The spec itself requires for many algorithms and containers, complexity requirements. So the implementers have to follow the requirements. So when you ask yourself for a certain operation, what is the cost? What is the complexity? You can either go to the spec, here are some links, or in most cases to CPP reference if you prefer not to read the spec language. But the links here are for both the spec and CPP reference right below. So let's get back to pushback into a vector. So there are two cases. It might be that we need resizing, and it might be that we do not. Now, in n pushback, in n calls to pushback, n minus 1 would not require resize, and only one would require. This is how vector is built. This is why it grows, it doubles when it needs, when the capacity is exhausted. And this means that the amortized pushback operation is indeed constant. An important side note, by the way, regarding vector resizing. We just talked about the fact that when we resize, when there is a need to allocate additional capacity, we need to move or copy the old values from the old allocation to the new one. And there is something that you have to bear in mind. If you have a move constructor and you forget to put the no except on it, vector would have to copy instead of move. And move is possible because we do not need the actual data on the old allocation. We just need it in the new allocation, so we prefer to move. But vector cannot move if move do not specify that it is not no except. So this one is important. There is a benchmark. I would not go into the benchmark, but if you forget to put no except on your move, then items would be copied and you pay for that. It's not complexity, by the way. The complexity is the same, n operations. Yeah, but it is n operations of copy instead of n operations of move. We always prefer the less costly one. Back to our quiz. Are you ready? Sorting a vector. What is the complexity of sorting a vector or sorting a list? Is it the same? What do you say, Adam?
Well, it's n log n, isn't it? But it's probably not the same for a list and for a vector. I mean, a vector has random access, a list doesn't. So although the asymptotic complexity is the same for both, it would be much more efficient to sort a vector. Also, not just that the vector has random access, it's also contiguous memory. I think you have a benchmark for that.
So I have a question for all of us. Suppose that we have a list and we need to sort the list. Maybe it might be more efficient to copy the list into a vector, sort the vector, then copy it back to the list. Now it sounds like insane. We are copying back and forth. Can it be more efficient? Well, complexity-wise, it's the same. It's n log n plus n plus n. You can ignore the additional n's. Well, it's not a complexity question, it's a practical question. And the practical answer is that, yeah, it might be more efficient. Actually, we have a benchmark, so let's take a look. In this case, sorting the list is much less efficient than copying to a vector. And of course, we do take into account the copying as part of the benchmark. So we test the benchmark and put inside the copying into the vector and back to the list, and still sorting the vector for the list is much more efficient, and still both are n log n. So you have to think not only about the complexity, but also on other things like, is it random access? Do we have memory locality? Memory locality is very important here. Let's go for another one. What is the complexity of finding the median of n items? The value that half of the items are below and the other half are above. What is the complexity for that? Adam, what do you say?
Well, the naive approach, if we have an array, right, and the array is unsorted, of course, we would sort it. We would pay n log n, and then we would find the item in the middle. If it's even, then, we will average the both middle items. But we can actually do it in linear time. Linear? Yes, linear. Okay, so there is an algorithm, PIC, and this is the paper, the original paper from 1972, and it shows us that we can actually get a linear time in the worst case. So for any input, we would get worst case linear time. However, there is another algorithm, quick select. We may know quick sort. It works in a similar manner. So in the quick select, we would just choose a random pivot, and we would partition our array. Now, since we're looking for the value in the middle, we would know where to continue. We would continue, at the first time, we would continue with the larger half, right? Unless we have exactly the middle. We partitioned in the middle. So we would go with the larger half, and then we would continue to partition and partition. However, it's easy to see that a random pivot, we can, due to bad luck, we can choose elements that would just, the smallest value or the largest value, and then we would get quadratic. We would get quadratic complexity. So it's worth mentioning that they are both linear on average, and that quick select is actually usually faster than PIC. In PIC, we partition to groups of 5, and then we find the median, and then the median of the median. So we do a better job in finding the pivot. Anyway, it is interesting that the one that has asymptotic, quadratic asymptotic is usually faster, and we might want to choose that. Also, it's worth mentioning that there's std nth element. And it's interesting that in the spec, it requires the implementers that the average complexity would be linear, but it allows the implementers to have quadratic worst case scenario. So that can give us a hint of what algorithm we can use.
So it means that in the spec knows that we can find the nth element in worst time complexity of On, and still the spec doesn't require that in order to allow the implementer to bring another algorithm which might have better practical performance. And this is the case with quick select compared to pick. So we may not pick. Let's go for another one. Unordered map. Find or insert in unordered map. What is the complexity? This is quite a tricky question. We are all, I think, have the perception that working with hash table or unordered map, find and insert should be constant. But what about our hash code? What can happen with the hash code?
Well, I mean, we can have a bad hash function, right? We can think about really bad hash functions, which always return the same, the same value. Okay, but let's disregard that. Let's say we have a good enough hash that gives us a uniform, somewhat uniform distribution. Even if we have a good hash function, if the domain of our keys is much larger, then maybe we have pathological bad data. And then, we are always sent to the same hash value. In that case, the worst case complexity of find or insert, we have to remember, right? If we already have the value, right, the key already, then we need to find it first to know not to add it. So we have a linear worst case complexity. But we do have a constant on average. And that's exactly what the spec requires.
So it means here that when we read in the spec or in CPP reference that find and insert, the worst case is On, we should not get too scary about that because, again, it is there because we might have pathological data that gets the same hash code. And this is something that even with a great hash function, if your keys domain is quite big, it either, as said, bad luck or some attack. So the spec should say that the worst case should be On, but again, the average is O1, and this is what we work with. This is what we think of when we are using unordered map. Speaking about hash, if we are implementing our own hash, it is very important to implement a good hash function that would have uniform distribution over the potential data that comes in. What about equality between two unordered maps? Now, this one relates to the previous question. So, to begin with, if the two unordered maps are not of the same size, different sizes, then it's constant. You just have to check the size. But suppose that the size is the same. So, if the size is the same, again, it might be that both unordered maps add pathological data, and it all sits in the same bucket. It all add the same hash code, not because of a bad hash function, but because this was the data. So the spec says the worst case is On square. But the actual average is On because, again, when you pick one item from the first unordered map, usually on average, you can just constantly, in constant complexity, check whether it appears on the other one or not. Okay, let's talk a bit about other examples. Some examples of constant complexity. Insert into a list at any position. Yeah, that's constant. You get an iterator where I want to add this item, and I just add it there. Erasing a single iterator in a list. Popping back an item from a vector from the end. You know that when you pop from a vector, then it does not shrink automatically. Otherwise, if it does, then we may say that it is amortized O1, but it is actual O1 because it doesn't shrink. You have to ask it to shrink if you want. Of n, linear complexity. Find, the stud find algorithm, max and min. They all need to iterate over all items. This is quite clear. What about log n? Binary search is log n because it is binary search. Find over a map because map is a binary tree. balance tree, insert into a map. All those are O of log n, and it says that in the specification. What about n log n? Well, stood sort, both for vector and list. O of n square, quadratic. Well, the example I have here is bubble sort, and the spec doesn't have bubble sort. I mean, C++, the library stud doesn't have bubble sort for good reasons. But should we, for any reason, implement our own bubble sort? Is there any reason whatsoever for using bubble sort? Maybe in space complexity it is better than, the other sorting algorithms that are around. Maybe it is stable. It is stable. Stable means that if we have two items which are equal, we preserve their original order. Yeah, bubble sort is stable. And bubble sort is constant in space complexity because it's in place. It is sorting in place without any need for additional storage or space. So maybe for these two features, these two attributes, it is better. Well, the answer is no. Don't use bubble sort. Because even if you need these two attributes, there are better sorting algorithms. Now, I will tell you why I put this slide here. Because I did see in actual production code people writing their own bubble sort because it's easy to write. And when you come to that and you say, why are you doing that and not calling sort? Oh, because, I just wanted to write it myself. I don't know why. But it's not efficient. It has no actual value for doing that. So don't do that. Do we have something to say about exponential? Yeah, I think we can say something.
Okay, so this is these are two examples of exponential time algorithms that we actually know that are not in p-time. Computing a perfect strategy for a generalized chess n-by-n board. That's the paper. Also, printing the power set of a set of size n, right? Printing every subset, right? The empty set and the set that every singleton and every set of size 2, etc., etc. That would also require exponential time. And just as a reference, think about finding a collision, or we have a value of a cryptographic hash function, and we want to find a collision. Then the best algorithm that I know is to brute force and try every option until we get something. If you have something better, please let us know. Maybe we can do something good for the world with it.
Or something good, for us. So, all those are exponential, and it means that it takes time to break them or to solve them. Let's talk about some of the items or the ideas that we raised. Ignoring the constant. Well, is it okay to ignore the constant? Let's take a look at this example. What is the complexity of this piece of code? We see here 2 loops. Should we count for the 2 loops, or only one of them is relevant for the complexity, the big O? Well, the first loop is on the data itself, which means it would grow as the data grows. The second one, the inner one, is to 100, which means it would not grow with the data. So do we have here quadratic complexity or linear? Yeah, it is linear, right? We have O of n. Now the question is, suppose that we can achieve the same thing with another algorithm, which time is n log n. And this n log n is it better than 100n? Because this side is 100n. The O is O of n because you just ignore the constant. But the question is, okay, I can ignore the constant, but I do not ignore the log. Which is better, n log n or 100n? Well, it depends on the input size. But then the question is, would we have input size for which log of the input size would be bigger than 100? Well, suppose that this is a vector on the current architecture that we're using. What is the biggest size of a vector on the current architecture, 64-bit, that we're currently using? Well, size t, which means the log would not be bigger than 64, which means that n log n on the current architecture would never exceed 100n. And in this case, it means that if you go with a simple complexity analysis, you may go with something that is not as efficient as you can have. Now, it's true that in some future architecture, might be that we can get a bigger vector. Yeah, but not in the current one. So yeah, if you take a look at that, log of vector size in the current architecture would not exceed 64. So yeah, n log n might be better than n. Two calls to STD algorithms. Suppose that we need to calculate something with two calls. Is it better if we write it ourselves in a single loop? Instead of using two calls to stud algorithms, maybe we can implement our own loop. Well, if we analyze that on complexity grounds, well, both are O of n, because n plus n, if t is n and another n, 2n is O(n). And the other one, okay, we have a loop, and in the loop we do two steps, two calls. One in order to calculate the sum, the other one in order to calculate the inner product, the sum square. So again, it's a loop, a single one, inside two operations. It's 2n and 2n, it's O(n) and O(n). So complexity-wise, it's the same. Is it the same also on practical grounds? Not necessarily. Well, we have to benchmark. Let's benchmark that. So we have a benchmark here for both a list and the vector. Suppose that we have a list and we have one single for each. This is right in the middle. Comparing to two calls to STD functions. This is to the left. Or two for each. I mean, instead of a single for each, we have two calls, two for each. Each one of them does the same calculation that we do in the one for each. One for each wins. Now, it is not necessarily the case always. Benchmarks are things that we have to check on your own architecture and actual data. But this is something that we have to bear in mind, that we lose mainly data locality when we do that one after the other. Now, by the way, there is another approach based on ranges. If you are using ranges, C++20, then two calls might be lazy attached into a single loop. So I have here an example, courtesy of my dear colleague Dvir Itzhaki, who also gave CppCon talk on 2019. This is the link. You should watch that, but this is not the subject of this talk, so I will go on. But ranges is a way to do that correctly. Some best practices. Let's discuss some best practices. Suppose that we have this, I see here, I think, complexity, quadratic complexity, and we need to improve performance. Where should you start? Where would you start, Adam?
I mean, if I have limited time, I would start with operation 2, because it happens, right, n squared times, while operation 1 is only performed n times.
Yeah, this is quite, everybody can see that you should start with operation 2, but in some cases you see people invest time when they see, complicated algorithm in the wrong place. Now, I'm not saying that you should not invest time in operation 1 if you have the time to analyze that. But first, if this is your bottleneck, operation 2 is much more important for improvement. That's quite easy to see. Breakout of loops. You have an algorithm. There is you can break out because you already found what you are looking for, or you are in your bubble sort, which you should not implement, and still you implemented. At least to have a flag that if there were no swaps in the inner loop, you can just break out of the outer loop. No need to continue. We are sorted. So having a break out of the loop is very important. It doesn't change the worst case complexity. It doesn't change it. But in practice, well, it has better performance. Breakout of loops or breakout of algorithms if you wait too long. And this is quite important. It is not related to algorithmic complexity, but if the algorithm took too much time, usually the other side, the caller, the user, the machine on the other side is not waiting there anymore. So have timeouts in your algorithms. Simple calls may hide non-constant complexity. In this simple example, well, it is not so simple. This piece of code that seems simple hides something that might be an additional loop. So the call to create, we have some kind of a static constructor, a factory for triggers, I don't know, something that creates a trigger and gets a row. Oh, this row, is it proportional on your data size? It means that it grows with your data size. Oh, so it means that you have here a nested loop which is related to your actual n. So this is quite quadratic, or m of n. You have to look at that. You cannot ignore something just because, oh, I didn't see a loop there. Well, it calls a loop. Time versus space complexity. Let's take an example. Max occurrences of an item in a vector. Let's assume this is a vector of strings. How would you implement the algorithm for max occurrences of an item? What is your thoughts about that?
I mean, we can sort the vector. It's a vector of strings. I mean, I'm guessing it's not items of constant.
No, it's strings.
It's okay. So, I mean, if it was constant, we could have done it in linear time. But if it's strings, for example, we can sort. Then we have n log n. Then we can traverse the vector, and we can count and see who appears the most. But, I mean, we can do it in linear time, right? Yeah. 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 I mean, we can. We can have a hash table, right? And we send every occurrence, and we count, right? We match the occurrence with how many times we counted. Okay. So, I mean, the average case for time complexity would be linear, but it would require linear space as well, right? Because we're building a table. However, the n log n case, right? We have the worst case would be n log n, but we can do it in place. We can sort in place, and we only need a constant space, right? We just need to count the max.
And we didn't discuss here the naive approach. So both have some attributes. One is better in space, one is better in time. There's also the naive approach of quadratic. Take the first one and then count on the entire thing, and then take the second one, in which case you pay both for space and for time complexity. Don't do the quadratic thing. So we have here two options, and you have here some kind of trade-off between time and space. Setup time. In some cases, we may add an additional unrequired operation, which is not part of the requirement, just to earn something later on. For example, the indexing in the previous slide. The index in the previous slide is an example. You are not required to index, yeah, but it helps me. I earn something. The efficiency is better. Another example of a setup time is, again, something that we talked already before, and so the benchmark, sorting a list. If you want to sort a list, in many cases, it would be better to copy the list into the vector, then sort the vector, then copy back to the list. And again, this is setup time, because the list would be sorted only after you copy it back from the vector. So all that you do aside is just copying, but because I have better time for that. Another very famous Stack Overflow question, I think one of the highest voted question is why it is better or has better time performance running over a sorted array doing something compared to unsorted when we do count the sorting itself as part of the time. And the reason that is described there in the answers is branch prediction. If the operation is related to the actual value that you run on, then when it is sorted, the branch prediction comes much better rather than you actually have randomness in your data. So in this case, yes, sorting might assist. Now, the data in Stack Overflow runs way back, and it was true with GCC version
4. It changes at 4.6.1.
So at 4.6, suddenly it is not so efficient to sort. Why? Because there are other optimizations that make it, you do not have to sort. It is more efficient not to sort. We have here 3 benchmarks. I will not go through them, but the first one is without any optimization. Without any optimization, well, sorting is better. And you pay for the sorting, and still, it is better. Why? Because without any optimization, sorting assists. It's good. But this is not a real good benchmark. When you do benchmark, you should do the benchmark as the actual production environment. And in actual production, you are using, I guess, optimizations. So the next 2, if there is a simple scenario optimization, well, the unsorted wins. But then if we complicate the code a bit, and the optimizer is not able to do, is doing their CMD. If the optimizer is not able to optimize the loop itself, then again, the pre-sort wins. So eventually what it says that setup time, doing some operation before, in some cases may assist, you have to benchmark. Picking the right container. The specification usually doesn't recommend things, but this recommendation comes from the spec. And I quote, the green background text is from the spec, and it rhymes. When choosing a container, remember, vector is best. Leave a comment to explain if you choose from the rest. This is from the spec. Yeah, somebody was a bit artistic. Prefer vector. If you go for unordered map, again, you should have a good hash code function, a good hash function. Using stood algorithms, don't reinvent the wheel, because if you do so, you might implement your bubble sort. To summarize, implications of bad algorithms and improper use of data structures are potentially much bigger than any micro-performance improvement. So, if you switch to a better algorithm, you may decrease your runtime dramatically. Thinking about algorithmic complexity is not pre-optimization. You probably heard about don't pre-optimize. Don't go for optimization before you know that you have a problem. Well, this is part of your design. And it is an essential element of your design and the ability of the system to scale. You cannot say, well, I'm writing bad code because otherwise it's pre-optimization. No, you should write good code. And choosing the proper algorithm, understanding the complexity of the algorithm that you're using is not pre-optimization, it's part of your design choices. The theoretical worst case big O shouldn't be your only decision factor. In real life, constants are important. 2n is better than 4n by a factor of 2. In real life, we might choose an algorithm with better average performance, even if its worst case complexity, it is not as good as the other one. And I think we show that with the median. Yeah, with the median and nth element. We prefer there some algorithm which has worst case complexity, because in practical life, it's better on average. Memory locality. Memory locality is very important. Very important. Stick to vector. We are using list. So maybe for some operations, copy the list to the vector, do something on the vector, copy back. Prior setup, sorting, indexing, in some cases, space versus time. A final note. We had a problem, right?
No, you have.
Well, the problem is that we are bounded by time. So we have a time complexity issue, and we didn't have enough time to talk about space complexity. So the final note in the summary is about space complexity. And specifically about space complexity that comes with conferences. When I'm back from a conference, my significant other usually asks me, how many shirts? So we have a conference wardrobe complexity problem, and I want to make it your problem. So I think the best student was you, and the best student would get a t-shirt for participating, and this would solve for the space complexity in your wardrobe. So in a moment, I'll bring you a shirt.
Okay.
And in the meanwhile, we are open for questions.
Thank you.
Just to present the shirt, this is a shirt from the core CPP conference that we have in Tel Aviv. We had it this year in person, on site, and the other side says, STD move doesn't move. So if you forget that, you should go to a mirror and try to take a look of what is on your back. You are participating quite well. So we have a winner here, and we are open for questions. Thank you. We have a question from online? Yes, please.
Okay, so the question from online is, hypothetically speaking, is it possible to have a constant time sorting algorithm?
Is it possible to have a constant time sorting algorithm? Yeah, if the data is bounded, if we know that the size of the data would not grow, but it's quite a bad answer. No, the answer is no. Adam says that we can even prove that it is not possible. Another question here or from online. I think that we have time for one additional last question. Yes, please. Okay, I think that I have to repeat the question and then maybe to try to understand it. The question was that we saw examples of going from quadratic to linear. Do you mean from the worst case to the average? Okay, I think the slide that you relate to is about amortized complexity. So there were two examples over there when we talked about amortized complexity. I'm just, getting back very quickly, and it will appear there on the question on pushback to a vector. So we discussed their amortized complexity, and we had two examples of, suppose that for n operations, the total worst case for each operation in the n operations is O of n squared, is quadratic. Then for a single operation, if I want to amortize that and ask, okay, what is the cost of a single operation complexity-wise? What is the big O? Then I would say that the big O is O of n for a single operation, even though it might be that for this specific single operation, I paid O n to the power of 2, O square, O n square. But for all the others, maybe I paid O1, maybe it was constant. So this is a discussion on amortized complexity. By the way, if you go to the paper, Tarjan, then there are 3 methods of calculating the amortized complexity. It is interesting. Thank you. Thank you for the questions. And we are here for additional discussion if anybody wants. Thank you very much.